Hey there, universe nerds. For decades, black holes were thought to be the ultimate cosmic prisons, regions of space where nothing, not even light, could escape. Once something crossed the event horizon, it was gone forever. But in the 1970s, physicist Stephen Hawking proposed something shocking. Black holes aren't completely black. They actually emit radiation. This idea, called Hawking radiation, changed our understanding of black holes and the universe itself. Today, let's dive into what Hawking radiation is, how it works, and why it means even black holes eventually die. The story begins with quantum mechanics. Space, as empty as it seems, is never truly empty. Thanks to quantum fluctuations, particles and antiparticles constantly pop in and out of existence in pairs, borrowing energy briefly from the vacuum. Normally, they annihilate each other instantly, disappearing back into nothing. But near the event horizon of a black hole, something special can happen. One particle falls in, the other escapes. To an outside observer, it looks as if the black hole is radiating energy. Hawking showed that this process makes black holes slowly lose mass. Over incredibly long timescales, they can shrink, fade, and eventually evaporate completely. For a stellar mass black hole, this would take far longer than the age of the universe. But for tiny black holes, if they exist, Hawking radiation could destroy them quickly. This was revolutionary. Black holes, once thought to be eternal, are actually temporary. The physics behind Hawking radiation ties together general relativity, quantum mechanics, and thermodynamics. Black holes aren't just cosmic traps. They have temperature, entropy, and obey the laws of thermodynamics. In fact, the smaller the black hole, the hotter it gets, radiating more strongly as it shrinks. At the end of its life, a black hole would release a final burst of energy, a cosmic firework, marking its death. This discovery also led to one of the biggest puzzles in physics, the black hole information paradox. If black holes evaporate, what happens to the information about everything that fell in? Quantum theory says information can't be destroyed, but if Hawking radiation carries no record of what was swallowed, then information seems lost. Resolving this paradox is one of the greatest unsolved problems in modern physics, with ideas ranging from holographic principles to wormholes. Hawking radiation has never been directly observed because the effect is tiny for large black holes. The cosmic microwave background, the faint glow of the Big Bang, is hotter than the radiation from most black holes, drowning it out. But indirect evidence and theoretical models strongly support it. Some researchers even try to simulate Hawking radiation in laboratories, using analog systems like sound waves in fluids or light in special materials to mimic black hole physics. If Hawking radiation is real, it reshapes our view of the universe. It means that over unimaginable timescales, black holes won't last forever. The massive ones left behind by stars will slowly fade. Even the supermassive giants at centers of galaxies will eventually evaporate. In the far, far future, after stars are gone, after galaxies are dark, black holes themselves will vanish, leaving only faint whispers of energy. The timescales are mind-boggling. A black hole the mass of the Sun would take about 10 to the 67th years to evaporate. The largest supermassive black holes could last 100 years or more. To put that in perspective, the universe today is only 1.38 times 10 to the 10th years old. That's like comparing a second to trillions of lifetimes. Hawking radiation shows us not just the fate of black holes, but the fate of everything across cosmic eternity. For Hawking himself, the theory was more than science. It was legacy. His insight bridged the gap between the infinitely large and the infinitely small, between relativity and quantum theory. While he became a cultural icon, his greatest contribution was showing us that black holes aren't forever. They too obey the rules of nature, slowly dissolving back into the fabric of space-time. So, do black holes die? Yes, but not in a way we can witness anytime soon. They don't explode violently, but they do fade quietly, radiating away bit by bit. Hawking radiation tells us that nothing lasts forever, not even the darkest giants of the cosmos. Next time you hear the words black hole, remember, they're not eternal prisons. They're temporary, finite, and ultimately destined to vanish, leaving the universe emptier and quieter still.